Okay, I think we'll start then. Every year we try and fit in a lecturer from our own campus here, and we usually pick someone who's actually done some really good work, and it has ended up in a very interesting scientific result that gets into one of the top scientific journals. And this is the case with the next speaker, Chris Rogers. So Chris Rogers was involved in the MICE project for a number of years. And just before I get to that, I'll just say a few words about who he is, in case a lot of you here don't know Chris. So he did physics at Somerville College in Oxford, and then he did a PhD at Imperial College with Ken Long. Ken Long should be in, Ken is in the audience here. And he got him involved in muon physics. I think it was right at the beginning of your PhD that you get involved in the Muon Ionization Experiment. He then joined the beams group at STFC Rutherford Appleton Laboratory. That's why he's the homegrown sort of expert in this area and speaking today. And he played a major role in the international design study for a neutrino factory. And one of the things that we talked about just before we came in here is, how long is it going to be before we see a neutrino factory? And Ken said, well, that's going to be my retirement project when I end my life here or at Imperial College. He's the project manager for the mouse code. I'm sure it's not pronounced that way, is it?
No, so it is indeed mouse.
Oh, is it? Okay, it's MAUS. Okay, so I got that right. And it's used really to simulate most particle accelerators. So if you're trying to build an accelerator, it's one of the sort of tools that you'd use to do that. So Chris is an expert in particle accelerators, and he is the lead author on a recent Nature paper, which was published about a month ago now. And that's why he's speaking today on muon ionization cooling, and will present the lecture on a bright future for muons. Chris.
Thank you. Okay, so thank you, Bob, for having me here today. It's a pleasure to talk to you all. Okay, so I'm going to start with particle accelerators. So particle accelerators have provided sort of unique insights into the nature of matter. So particle accelerators have told us, more or less since they're invented, what matter is made of, what generates the forces between that matter, and the real culmination of a project which has spanned the best part of a century has really been the Large Hadron Collider, which we all know at CERN, where we've discovered the Higgs particle. Now, in particle physics field, there are many open questions remaining. So why do different particles have such radically different masses? We have neutrinos, which are these extremely light particles, and we have the top particle, which has a mass which is, thousands, millions of times heavier than neutrinos. Why is this? Why are different particles sensitive to different forces? So neutrinos, again, are sensitive to the weak force, and we believe the gravity force. But then quarks, protons are sensitive to strong force and electromagnetic force. Why is this? Also, why is there so little antimatter in the universe? Why, when we look up into the cosmos, do we see matter but not much antimatter? Are there any undiscovered fundamental particles out there which we haven't seen? And indeed, what's dark matter? Maybe that is an undiscovered fundamental particle. So with particle accelerators, we can study these things. There's a problem. So as we've gone through the previous century and explored these questions, we've needed bigger and bigger particle accelerators. And that means going to higher and higher energies with our particles. So that becomes difficult. So why is it hard to build particle accelerators with higher and higher energies? Well, proton colliders, when we make a proton collider, we need to send these protons, we need to accelerate them up, we need to store them, and in order to store them, we need to bend them using magnets. And in order to store higher and higher energies, you need stronger and stronger magnets. With electron linear colliders, we need to accelerate the electrons. So if we have a straight accelerator, we need to accelerate those electrons, and it's very hard to accelerate them quickly enough. With circular electron colliders, They have similar problems to the protons, but there's another problem. As you accelerate electrons, they radiate X-rays. And that means that as you bring energy into those electrons, they dump it all out again in X-rays, and so we can't accelerate the electrons to as high energies as we'd like to. So the sorts of proposals we've seen for the next generation of particle accelerators involve, huge beasts. And so the question which I'm going to address today is there a better way? But to answer that, I'm going to go back to the origins of particle physics. Okay. So in the 1930s, actually what I just said is wrong, because in the 1930s we had the answer. In the 1930s, physicists had identified all of the constituents of matter. So we had protons, which are in the atomic nucleus. We had neutrons, which is the other part of the atomic nucleus. And we had electrons, which give us chemistry. Job's done. There was a problem, and the problem was cosmic rays. So a couple of guys at Berkeley Lab, Anderson and Neddermeyer, were looking at atmospheric radiation. So they had a cloud chamber. As atmospheric radiation came down through the cloud chamber, it left a little track. Now, if they put a magnetic field on that cloud chamber, the trajectory of those charged particles would bend. And higher energy rays are bent more, higher energy rays are bent less because of the effect of the field. So then what they did is they measured the amount of bending before and after passing through a 1 centimeter thickness piece of platinum. And this is what they saw. So they saw an interesting feature. So they actually saw two different populations of particles. So they saw this sort of this shaded population of particles. So these guys are accompanied by what's called a shower. So you see these tracks going through the platinum. On the far side of the platinum, you've got loads of noise, loads of mess on the other side, which we call a shower. The other feature is that they lose lots of energy as they go through the platinum. They lose lots of energy, which means that they bend more as they go through the platinum. They saw another population which hardly lose any energy and are not accompanied by a shower. And that's interesting. Later, they had discovered muons. And so later on, people named this population here muons, this population electrons. So Rabi, the discoverer of NMR, his comment was, well, we understand physics. Who ordered that? The answer is, lots of people, in fact. So material scientists, archaeologists, chemists, physicists, atmospheric physicists. And it turns out that muons are pretty useful. So let me just explain a little bit more about muons. So muons are fundamental particles. So this is a picture of all of the different fundamental particles. So we have quarks, which form the protons and neutrons and other nuclear particles. We have leptons, which electrons are a sort of lepton. They go around the outside of the nucleus. We also have muons, tauons, and neutrinos. We have the bosons, which are the force carriers. So muons are a fundamental particle. So this is arranged in order of mass. So these guys are heavier, these guys are lighter. So the muon is about 200 times heavier than the electron, and it's unstable. It has a 2 microsecond lifetime. So where do these atmospheric muons come from? So what Anderson and Neddermeyer were observing were natural muons coming from cosmic rays. So a cosmic proton was striking the atmosphere. The proton was hitting an atom in the air, breaking it up and making a thing called a pion, which is 2 quarks stuck together. The pion decays radioactively in about 30 nanoseconds and makes a muon. And the muon comes down and hits the ground. And they detect it in their detectors. It actually turns out you have a muon traveling through you right now. So you typically have about a muon traveling through you every second. So they're not uncommon. And you can use these muons for some interesting physics. So Alvarez, who we'll meet again later on, had a neat trick. So he wanted to know about the pyramids. And so this is a cartoon written by a chap from the University of Minnesota in the 1970s. And in case you can't read the words, I've pulled them out. So the pyramids, it says, were built as royal tombs with remarkable accuracy. Of the 2 largest near Cairo, Cheops has chambers inside the pyramid itself, but in Khafre, only a subterranean chamber has been found. well, this sounds exciting. Professor Alvarez of Berkeley suspects there are other hollow vaults, and will use a spark chamber in the subterranean passage to X-ray the pyramid with incoming cosmic rays. Now, unfortunately, our colleague from the University of Minnesota said that he was going to X-ray them, but of course, Alvarez wasn't using X-rays, he was using muons. So he was looking at it, he placed a spark chamber in the middle of the pyramid, somewhere in here, and looked to see how those muons would go through the pyramid. And so this is what he saw. What he's doing, he's just counting muons, and these numbers here, the number of standard deviations above the expectation, around the expectation. If he sees a big, lots of a significant event, then you expect to see 5, 6 sigma deviations from the noise. He didn't see anything. So therefore, unfortunately, he didn't see another chamber. But nonetheless, muons have an interesting property, which they're very highly penetrating. There's another thing which we can do with muons. Actually, this one's taken from last year. So we can directly probe the atmosphere. So this is an example of some colleagues from India who were looking at thunderstorms. They had a cosmic ray detector. So each of these EFM things is actually is a detector. And the thundercloud moved across their detector system. And what they did is they looked at the change in the muon flux as the cloud moved across their detector system. And by looking at the change in the muon flux, they could estimate what the voltage in the air above their detectors was. And so they actually were able to measure or estimate the voltage which came from the thundercloud. So then that's a neat trick. Now, their resolution is limited by, there's some systematic errors, but they're also limited by rate. So we ask ourselves, well, can we make more muons? And the answer is yes. So muons, we know in the atmosphere they're produced by these cosmic protons and other ions hitting the atmosphere. Well, we can do that in our accelerators. So we can take a beam of protons, we can put that beam of protons onto a target, and then we do exactly the same thing. We get a pion coming off and some other stuff, and then that pion decays radioactively into a muon and another particle called neutrino. So we can get a much more intense muon source this way. And in fact, that's what they're doing, I guess, right now over on the other side of the campus at ISIS. So this is ISIS. So we make a beam of H- ions. We accelerate those H- ions into the synchrotron, make the protons. The protons then come down one of these EPB lines, extraction lines. They hit a target. And so there are two targets. This one produces neutrons. This one, they're looking at muons. So this is a muon target. Okay, and so when you have a more intense muon beam, you can do some interesting things. So this is some work which was done, some of it was done at Rutherford Lab. So you can inject muons into a cell containing deuterium and tritium in a mixture. What happens is the muon hits that deuterium tritium ions and displaces the electrons. So instead of having DT plus, where you have an electron in that ion, you have DT plus, where you have a muon instead. And that means that the deuteron and the triton move much closer. And that means the nuclei are so close together that you can get them to overlap and you get cold fusion. And this is a neat trick. And the even neater trick is that the muon is still available to make another fusion. So this is a catalyst reaction. The muon stays alive, hits another DT ion, makes another reaction, and then stays alive and hits another DT ion and makes another reaction. So you can get muon catalyzed fusion. And then the work which was done at Rutherford Lab, you can characterize the fusion by the rate of fusions, the number of times you form one of these DT muonic ions, and the loss probability per fusion. So sometimes the muon doesn't stick, and so the probability is a fraction of a %, but nonetheless you lose some of the muons. And so this was studied on ISIS at the Rick and Rel beamline, and they looked at things like dependence on temperature, dependence on density, and dependence on the concentration of DT. So the problem is that they were limited here by the available muon source. So the energy cost to produce muons was too high. So if you try to produce energy this way, nuclear fusion for a fusion reactor, you can't do it. because you invest so much energy in making the muons, it's not efficient. Another example of use of muons on ISIS with this more intense muon source is muon spin spectroscopy. So here you have very low energy polarized muons which you embed in a material. The muon polarization then is affected by the local magnetic field, and you can measure that polarization by examining the direction the decay electrons travel in. So if you imagine you've got muons coming down onto a material, they get stuck in the middle of the material, and then they decay, and you get a positron coming out and hitting a detector. That way you can figure out what's going on inside your material. So for example, you can study things like the magnet penetration depth in a superconductor. So this is a signal which they took from using this muon spin spectroscopy. So what's going on here is that a muon has become embedded in the material and started rotating with a Larmor rotation in the magnetic field in the superconductor. And so if you then look at the decay products, you can see that the decay products, you can actually see the spin oscillating by looking at the decay products. And they've got various different things they're looking at. So they're looking at different pressures, and they're looking at different temperatures. And you, by looking at the precession rate of the Larmor precession, you can tell something about the strength of the magnetic field. And they're also looking at depolarization, which tells you something about the spread in the field, how regular the field is. And in this paper, they're looking at the band structure in high temperature superconductors. So it's quite an interesting technique. Other things which coming back to particle physics, other things which people look at, again using muon magnetic moment, is to look at the magnetic dipole moment. So the magnetic dipole moment is predicted by particle physics, but the measured value is inconsistent with the prediction at a few sigma. So this plot shows the historical growth in precision of the measurements. So they've got various different measurement campaigns in this experiment and previous experiments as well. And what you can see is that as they increase the precision, they see that the experiment and the theory, the dashed line is the theory, disagrees at several sigma. And this is a neat measurement because it's sensitive to energy scales beyond the LHC. So you can have physics processes which are happening way up at high energies which affect the magnetic moment, and so you can make measurements beyond the energy scale of the LHC. Okay. Another important physics which you can do with muons is looking at neutrino decay products. So neutrinos are fundamental particles. There are three types of neutrino. There's a neutrino for the electron, neutrino for the muon, and neutrino for the tau particle. And the neutrinos can change from one type to another. And that's an interesting feature because it could be a source of matter-antimatter asymmetry. So we can use muons to generate these neutrinos, and we get a very nice, well-characterized muon source. So this is an example of a proposed neutrino source. So this is an example of a proposal at CERN where we have protons coming around the bend. They hit a target and make pions, and then the pions go around the storage ring. They decay very quickly in the first straight, in fact, and we make muons. And then we store those muons, and we let the muons decay to make neutrinos. That allows us to make a precise measurements of neutrino interactions, which can help with some of the neutrino oscillation facilities. And this facility is called NuStorm, and it's been proposed for CERN, for CERN or Fermilab, in fact. And we can also make a precise probe of neutrino oscillations using something called a neutrino factory. So if we want to probe the neutrino oscillations directly, we need to accelerate the muons before they decay. That's an interesting challenge. Okay. So, muons. Muons, then to summarize, they have a half-life, 2.2 microseconds. They're naturally occurring from cosmic rays, and we can artificially manufacture them by first making these pions, and then the pions decay to muons, and then we use the muons. And there are many uses. I showed archaeology, meteorology, material science, particle physics, but there are other things. One can produce them using photons, one can produce them using electrons, one can do muon cancer therapy. Controversially, it's been suggested that atmospheric muons can affect the climate. There's also a possibility for looking at direct decay of muons to electrons in something called lepton flavor violation. But I sold you in the first slide on colliders. So what about colliders? Let me go back there. So back to the future. So as I said, there's this effort to explore phenomena at higher and higher energies. And that corresponds to smaller and smaller scales. So atomic physics and then subatomic physics. I've lost the date. Okay. Unfortunately, this plot's come out wrong. I suspect there's a conversion error somewhere. But so we can learn about the constituents of matter. I'll skip over the plot. So what I was trying to show, maybe I'll stay on the slide. What I was trying to show is that as we've gone forwards in time, the energy of colliders has grown exponentially in time, and the problem is that this exponential growth is very challenging to maintain. And so the scale's obviously decided to squish itself, which is unfortunate. But as time's gone on, the energy scale of the accelerators has grown exponentially, which means making the field stronger for proton accelerators, or making the ring bigger and bigger and bigger for a circular type accelerator, and that's challenging. So remember, the proton colliders are limited by magnetic field strength, which limits the bending radius and hence the tunnel length. And electron rings are limited by synchrotron radiation. So we lose energy to X-rays, and that means that we can't stick energy quickly enough into the electrons. So synchrotron radiation is much stronger for low mass particles, and that's going to be important. The other thing is the linacs are limited by the available acceleration. So we need incredibly long tunnels to accelerate electrons in linacs. Okay, so as an example of the circular colliders, so this is I've put 3 different circular colliders on this plot, on this picture. So this is the LHC, which we all know, 27 kilometer circumference, 14 TeV proton-proton collisions design, and in the same tunnel there was also LEP, which had 200 GeV electron-positron collisions, and that's sort of the limit for electron-positron collisions. So I put the tevatron up here. The tevatron was in Chicago, so it doesn't fit on the map, but that was 6.2 kilometer circumference and 2 TeV proton-antiproton collisions. And the FCC is this thing. So the FCC is a proposal which would give us up to a few hundred GeV electron-positron collisions. I note the electron-positron collisions are not that much higher energy than LEP, and that's because of the synchrotron radiation limit. Or you could go up to 100 TeV proton-proton collisions. The circumference of this beast is about 100 kilometers. So if you've never been to Geneva, this is La Salève. So this is a mountain. There's a fantastic view from the top. So there's a cable car which goes up from Geneva up to the top of La Salève. It's amazing. If you ever go to Geneva, I recommend it. There's this great, and from Geneva, you can see this massive cliff. So you can just look down, and it's a sheer drop of several hundred meters. The point is, though, FCC has to dodge the mountain. It's a big enough collider that you have to dodge mountains, which is an impressive thought. Okay, another example is this is what the proposal for linear colliders at CERN would look like. So again, this is the LHC. So this is CLIC. So there's a lower energy version of CLIC, which is 380 GeV, and then they've got proposals for higher and higher energies. Again, okay, so this is going underneath the Jura mountains, and again, you're building tunnels under mountains. It can be quite challenging. So the scale of these things, the LHC is big, and the scale of these things is bigger. Okay. So protons. So there's a trick. So what we want to do, we want to make a sneaky trick. So proton collisions have a lot of wasted energy. So protons are made up of subparticles, gluons, quarks, and when you collide protons together, most of the energy is lost in non-colliding particles. So what we would like is a fundamental particle which doesn't experience synchrotron radiation, but because it's fundamental, we don't suffer this problem. So we don't lose all of this energy to the quarks which don't collide. That's muons. That's muons. So that's the trick which we want to use. And it turns out we can do some very nice physics with muons. So this plot shows the physics reach of muons compared to protons. So there's two lines. So the blue line is assuming that whatever physics process you want to look at actually happens 10 times less often with muons than with protons. And what this tells you is that a 14 TeV muon would get you the same reaction rate as a 100 TeV proton. And if you assume that the interaction rate is the same, is equivalent, then actually a 14 TeV muon would give you more like 200 TeV protons. So muons can give you an equivalent, much higher energy than protons in a collider. So what would a muon collider look like? Large muon collider. So we have, to make muons, remember we need to put protons onto a target. So we have a megawatt class proton driver. The megawatt class proton driver, then we make a very powerful beam of protons. We put those protons onto a target. We produce pions, and the pions decay to muons. The muons are then captured and cooled, and then we can accelerate them up to TeV scale. So I'll tell you a little bit more about what cooling is in a moment. And then, so we accelerate them up to TeV scale, we put them into a collider ring, and then we collide them. So there's two critical issues which need to be addressed to make this work. Two challenges. So the first is that muons have a very short lifetime, and the second is that the initial beam emittance of the muon beam is very high, which is also the same as saying that the beam has low brightness. Okay, so over the last 2 decades, there's been considerable hardware effort towards bringing a muon accelerator to reality. So Merit was a test facility for testing targetry for a megawatt class target. So they put protons onto a mercury jet. Now, there are challenges with these megawatt proton beams to do with things like containing mercury, if you want to, or not destroying the target. Megawatt targets are hard. So they built Merit to try and address these issues. They actually were looking at using liquid mercury, which is the technology used at SNS, and they wanted to put the target in a 12 Tesla field, a strong magnet, in order to capture as many pions as possible. And so they demonstrated these principles using a test rig at CERN in sort of the mid-2000s. EMMA, which many of you will know, was built at Daresbury Lab. Here they demonstrated fast acceleration. So using a synchrotron like the LHC, it's very hard to accelerate muons within this 2 microsecond lifetime. So what we need to use is something which doesn't involve ramping magnets. So the LHC, the real challenge is ramping the magnets within the lifetime of the muon. So with EMMA, we demonstrated fast acceleration using fixed field accelerators, FFAs. MuCool was a test facility built at Fermilab. The idea was to test radio frequency accelerating cavities. In particular, we were worried about RF, this radio frequency cavities in high magnetic fields. And so we were looking at ways of stopping sparks in the cavities, breakdown. And so we tried doing breakdown suppression using high pressure gas. We also looked at very careful design of the RF cavity, very careful cleaning of the surfaces. And in fact, we were able to successfully demonstrate operation of cavities with very strong magnetic fields. Now, the reason we need cavities with strong magnetic fields, I'll come to in a moment. The final piece of the jigsaw then was a Muon Ionization Cooling Experiment, mice. So this is how, this is demonstrating a technique we propose to increase the beam brightness. So unless we can increase the beam brightness, the particles don't collide. They just miss each other. So we need to increase the beam brightness to make a collider. The technique we wanted to use was ionization cooling. So let me talk a little bit about beam brightness and emittance. So let's say we're making muons, okay? So we have a nice orderly beam of protons, which our colleagues in the proton accelerator world have given us. We put those protons onto a target, and the pions coming off the target are going in all sorts of different directions because these sort of nuclear interactions are a messy process. The pions then decay into many different positions, so we end up with muons which have lots of different positions, lots of different momenta, going in all sorts of different directions. And so that's a beam which has low brightness and what we call high emittance. Okay. So if you just think of a beam as a cloud of particles, the particles are moving in lots of different directions. The particles have a big spread in position. We can use a magnetic lens to focus the beam, which means we decrease the spread in position, and we increase the spread in momentum. Or we can use a magnetic lens to defocus the beam, which means increasing the spread in position, decreasing the spread in momentum. The point is, if this ellipse represents the area occupied by the beam, we can squeeze it any which way we like, but the area of this beam in momentum position space is a conserved quantity. So the emittance is a conserved quantity. It's sort of analogous to temperature or disorder or something like this. So in a normal magnetic lattice, this emittance is conserved. Now, there are cooling techniques which exist to reduce emittance. So for example, we can pass two beams close to each other with different emittance. So a hot beam and a cool beam, and the heat transfers from the hot beam to the cool beam. This electron cooling is an example of this. Or we can measure random noise in the beam and then apply compensating kicks for that random noise, and that's something called stochastic cooling. And so this is actually an example of stochastic cooling. This is Vandermeer's plot from his Nobel lecture. So what you have here is initially a very broad beam. This is taken from a scope trace, by the way. And what you have at the end is a very thin beam. And so this is after cycling the beam for an hour or something like this. And you can cool the beam. So I think having spent 2 years analyzing data, I think it's lovely to have an experiment where you can just take the scope trace. Anyway, so the problem with these cooling techniques is the time scale is minutes or hours. And remember, the muon lifetime is 2 microseconds. So what do we do? So ionization cooling is what we do. So we put the beam, so these are your muons going all sorts of different directions with all sorts of different positions. We put them through an absorber. If you see what happens when we go through an absorber, well, the momentum's reduced. So if the length of this line is the momentum, well, these lines get shorter. And that's cooling, incidentally. And then we put the beam through an RF cavity. The RF cavity brings the beam, accelerates the beam, but only in the longitudinal direction. So we end up with a beam which maybe has the same energy, but is all going in a much more uniform direction. And that's cooling. So we end up with a beam that's more straight. Now, that's obviously sounds very nice, but multiple Coulomb scattering ruins the effect. So this is where a muon hits the nucleus, bounces off in a random direction. And so that tends to cause heating. And so we can mitigate this effect either by using tight focusing. So that means having very strong magnets, which you use to squeeze the beam down as it goes over the absorber, or by using low Z materials, so materials having low atomic number. So a low atomic number material has a small nucleus, doesn't scatter as much, but we still get the same energy loss. Okay. So cooling. So this is an example of an ionization cooling lattice. So this is the sort of thing we would be talking about. So you have RF with these absorbers on the absorber windows. So this is the absorber here. It's lithium hydride, so low Z. Lithium's atomic number 3, I think. And you have superconducting coils. And so the superconducting coils provide this really tight squeezing, and then you need to put the energy back in. So you need these RF cavities. So it's a very compact lattice. This stuff is all squeezed together into a few centimeters, few tens of centimeters. The fields are very strong, and you'll note that for some, to make the lattice work better, we've had to reverse the direction of these coils. So you've got these big forces between these coils, which have got strong enough fields that the forces are tens of tons. The big aperture coils as well, so 350 millimeter radius. And then you've got this really high gradient RF, which you're putting next to it all. And so in this example, so this is the sort of cooling performance which you expect. So transverse emittance as a function of distance. And so you've got some capture here, and then this is the ionization cooling. And you get this really nice cooling performance where the emittance drops by a factor of 3 or 4. So it seems to work. This is a simulation, I should say, but it seems to work. Okay. So how can we get these muon beams which start off with this huge emittance so that we can accelerate them? The answer is ionization cooling. All of these ionization cooling lattices share some common principles. They're all very compact. They all have low Z absorbers, so the one I just showed was lithium hydride, but liquid hydrogen, hydrogen is atomic number 1, so that's very low Z. Very low Z absorber. So liquid hydrogen or lithium hydride are typically what's proposed. And the other thing they typically have is superconducting solenoids to get this really tight focusing. So we want to demonstrate this technique, that such a lattice can work. And the way we've done that is Muon Ionization Cooling Experiment, and the collaboration is the International Muon Ionization Cooling Experiment collaboration. So, questions we want to answer. Can we safely operate liquid hydrogen absorbers? Can we operate such a tightly packed lattice? Do we see the emittance change we expect? Do we see the transmission we expect? So this is what mice looks like, the experiment. So we have some diagnostics upstream, which I'll explain in a moment. We have a diffuser, which allows us to select the beam emittance. And these are superconducting coils here. So we have these very strong superconducting magnets. We have a detector to measure the beam upstream of the experiment. Then we go through an absorber. And then we have a detector to measure the beam downstream of the experiment. And then we go through some more diagnostics. So the basic principle is to measure the beam upstream, go through this absorber to cool the beam, and then measure the beam downstream. This is what it looks like in reality. So again, we have this diagnostics, the TOF detector upstream. Then we have a superconducting solenoid. Inside here is the tracker. Then we have the absorber, which does the cooling in here. Then we have another tracker down here to measure the beam coming out. And then we have some more diagnostics downstream. Okay, so mice, we had over 100 collaborators, 10 countries, 30 institutions. So if you know the site, so this is Diamond here, this is R1, R2, and this is the ISIS ring. And so mice was down here next to ISIS. So we had a dedicated transport line which brought pions, which decayed and made muons from the ISIS synchrotron into the mice hall. We ran between 2008 and 2017. Okay, so just to reiterate, the configuration was to measure the muon position and momentum upstream. That's our emittance, remember, muon, the position and momentum. Cool the beam using some absorbers, and then measure the position and momentum downstream to get the emittance out downstream. So this is what the beamline looked like, which took the muons from ISIS into the experiment. So we designed a beamline which could take muon with momenta ranging between 120 and 260 MeV over C. So we had emittances between 2 millimeters and 10 millimeters. And we were able to suppress the pion impurity very well. So we could operate in various different modes. We could have a high rate mode, which had lots of pion impurities, or we could have a low rate mode where we had a very pure muon beam. So we had these very strong superconducting magnets. So we had spectrometer solenoids upstream and downstream of the absorber. So these were 400 millimeter diameter bore magnets. So it's a 5-coil assembly. The first 3 coils are there to give us a uniform solenoid field. And then we had 2 more coils which let us control the beam as it goes into the absorber. Then wrapped around the absorber, we had some what we called focus coils, which gave us this final really tight focus on the absorber module. And this is a dual coil assembly because we wanted to be able to flip the polarity, so to go from a positive field to a negative field in the absorber, or stay at positive field all the way through. So this is what the absorbers look like. So in fact, we used 3 different absorbers. So we had a 65 millimeter thick lithium hydride disc. So this is the liquid hydrogen absorber. So it's all wrapped in MLI, multi-layer insulation. But inside here, there's this beautiful liquid hydrogen container. So because we're trying to reduce the amount of high Z materials, we need these really thin windows, so a few hundred micron thick windows to contain the liquid hydrogen. So we had to make these very elegant, very carefully molded liquid hydrogen windows to try and contain the absorber. And then also we wanted we wanted to look at what happened when we stuck a wedge-shaped absorber into the beam, where we get different energy loss across this beam. So high energy loss on the side, where it's thick, and low energy loss in the middle, and no energy loss at all on the other side. So the diagnostics. So we had 3 scintillating TOF stations. They gave us this very nice time resolution, a few tens of picoseconds, and we commissioned those in 2009. We had 2 scintillating fiber trackers. They gave us a position resolution, again, a few hundred microns, and momentum resolution of a few MeV over C. We used a threshold Cherenkov counter and a pre-shower detector and another totally active scintillator to measure the beam coming out of the experiment. So this is the scintillating fiber tracker. So what happens is the beam comes down through these fibers. It's immersed in a solenoid field. So the solenoid field means that the muons take a helical path as they go through the tracker, and by looking at the shape of that helix, we can reconstruct what the momentum of the particles was. So the scintillating fiber tracker was based on D0 technology. We had 5 stations. We got a very good position resolution. So 500 micron position resolution, 700 microns if you include scattering effects. So it depends on how you count it. And a few MeV over C momentum resolution. And the precision on emittance was 10 to the minus 3 level. So it's a very precise detector. The TOF, so we had 3 time-of-flight stations. So these were each constructed by putting 2 planes of scintillator bars together, and then reading out either end with PMTs. And we were able to measure a 50 picosecond time resolution. So very nice time resolution. We needed the TOFs to give us the particle identification. So what we did, if we have 2 TOF detectors, we know how far apart they are, so we measure the time the muons go through, and then we use the distance to calculate the velocity. Now the tracker, this helical tracker, gives us the momentum. So by comparing momentum with velocity, we can figure out the mass of the particles. Mass means particle identification. So we could exclude electrons that way, and pions. We also had some other detectors which we used to validate the principal detectors. So we had the Cherenkov threshold detector. These were twin aerogel slabs. They had different refractive indices, and because they had different refractive indices, when pions go through, you get light at certain momenta, and you get, when muons go through, you get light at other momenta, and by looking at whether there's light coming out of the detectors, we're able to decide whether we have muons or pions. And they corroborate the TOF velocity measurement. The KL was a sampling calorimeter, so we had extruded lead foils interspersed with scintillating fibers, and it both provided a pre-shower for the EMR. It also gave us some rejection for electrons from the downstream measurements, and we also used it to look at the pion purity of the beamline. Then the EMR, so this was a totally active scintillator. So you've got these, so this is a 1 meter by 1 meter square, a cube of totally active scintillator, read out at both ends, and it allowed us to examine the properties of the particles we were detecting. And what you can do is you can reconstruct these very nice tracks. So this is a muon coming in, the muon stops, and then it decays to a positron, to an electron. So you can use this detector to identify muons or electrons and figure out what the particles are going through your experiment. Okay, so we took data between 2008 and 2017. This is a picture of our control room. So we measured various things. We looked at the scattering which we got in the absorber. We looked at the energy loss we got in the absorber. And then we looked at the emittance change. And the particle-by-particle beam reconstruction which we used was kind of unique. So what we're doing in the experiment is we're firing one particle through. We're measuring the position of momentum upstream, position of momentum downstream, and then another particle goes through, and we do the same thing. Whereas in a normal beam physics experiment, you expect to measure, you know, 1 trillion particles going through your detector, which was not what we were doing. And so we would accumulate these single particle tracks over an hour, 2 hours, 3 hours, and build up a picture of how the beam was going through the experiment. So that gave us incredible power for resolving some things which you never see in a normal accelerated physics experiment. So we could look, for example, at correlations between position and momentum at this very fine level of detail. So as an example, you can see, we could see this correlation between position, so this is vertical position here, and horizontal momentum, and horizontal position and vertical momentum here, which comes from the solenoid field. So as particles go through a solenoid field, they spin. And so they get this really nice coupling, we call it, or angular momentum, which we can measure. And that's something which is very hard to measure using normal accelerated physics techniques. So it's very nice experiment. You know, in the end, we're trying to look at emittance. So what we're trying to do is reconstruct the amplitude, which is like a single particle analog of the emittance. So if you imagine this is your particle beam here, position and momentum, then what you can do is you can make these ellipses, and by looking at the position of the particle, the area enclosed in the ellipse, then you can figure out, you can associate with each particle an amplitude, which is like sort of single particle emittance. And the mean of that amplitude distribution is what we call the RMS emittance, or beam emittance. So ionization cooling, then, we want to see a reduction in that beam amplitude. So this is an example of then using, when we use all of those tracks together, we can measure the emittance. So this is an example from one of our papers where we measured the 4-dimensional beam emittance, that's like the mean amplitude, including the XY coupling terms. And because we have this particle-by-particle reconstruction, we can do things like we can slice the beam in longitudinal momentum to understand effect of, well, if you're going through bending magnets, as we have in our beamline, that can introduce correlations between longitudinal momentum and emittance and things. So we're able to do some very neat stuff with our diagnostics. What we wanted to do, though, was look at the change in amplitude. And so that's what I'm coming to next. So remember, the aim of the experiment is to decrease the beam emittance. So what we wanted to show was that the amplitudes, in the core of the beam, there are more particles with low amplitude after the experiment than before. Okay? So what I've got on this plot is 4 different absorber settings. So we've got the empty liquid hydrogen, so that means we've just got the windows and vacuum in between, helium gas, I should say. We've got full liquid hydrogen, so that's just the windows and liquid hydrogen filling the windows. And we've got no absorber, so we didn't have anything in there. We've got lithium hydride. And so what you can see is that upstream, when we have no absorber in, the distribution of amplitudes, the number of particles having low amplitude, is the same. So we haven't seen any change in the amplitude distribution with no absorber in. So out here, we have scraping. So the reason we lose particles here is because particles are hitting the edge of our experiment. Okay? So then if we have an absorber inside the experiment, so we stick the liquid hydrogen in, for example, then downstream we see we have more particles in the middle after the experiment than before. So the green line is above the red line. And if we go to a larger emittance beam, so this is a low emittance beam, and this is a high emittance beam. If we go to a larger emittance beam, we get a stronger cooling effect, which is exactly what we expect. And the reason is because with larger emittances, you have a bigger momentum spread. And so the relative decrease in momentum is actually larger. So that's exactly what we expect to see, and it is what we see. So you have this very nice effect and it's consistent with, we see an increase in the number of core muons, and it's consistent with what we expect. So I just wanted to show as well the ratio of the two plots on the previous slide. So what I'm going to show on what that picture was, just the ratio of these two numbers. Okay, just to make it clearer. So what we have here is again for empty liquid hydrogen, full liquid hydrogen, no absorber, and lithium hydride, low emittance and high emittance. The 140 incidentally is 140 MeV over C. That's the momentum. And what you see is that at low emittance, the number of muons increases. So that's exactly what we want to see. So the ratio, there's more downstream than upstream, which means this ratio is greater than 1. And so the blue line is data. The reason this one's interesting is because the red line is simulation. And actually, we get a very nice agreement between data and simulation. So we not only have we shown the effect, but we understand it. And that's really important, because when we're doing all of this accelerator design, we're relying heavily on simulation. So if we don't understand if the simulation doesn't explain what we see, then we don't have anything. So it works. So we've demonstrated cooling. Okay. So I just wanted, before I finish, I want to have one slide just to say where we could go to next. So to build a muon collider, we need lots of cooling. So we need to reduce both transverse emittance, so this is transverse momenta and position, and longitudinal emittance, so the length of the beam along the beam line and the spread in longitudinal momentum. So mice, as I explored, only really the initial part of a muon cooling channel. So this is a sort of sample of one particular muon collider, and this is the regime mice has explored. And really, we focused on the transverse emittance, and we haven't looked too much at the longitudinal emittance yet, although we have some data in the bank on that. So then the question is, well, can we explore a bigger range of the cooling space? And so one concept which one could consider is to look at a cooling ring. So this is the sort of ring which one could build. And there, the advantage of a cooling ring is we send the muons round many times or some other particle, then we can recycle the cooling apparatus and get a stronger signal. So I think as a next step, we would need to try and explore this regime, and a cooling ring is one way to take that, to approach that. So, muons are fascinating particles. In fact, they've got loads of applications. I only touched on the surface, really, of what muons can do. And you know, if we can deliver a muon beam, then I think there's lots of other things no one's thought of yet. It's very clear that the properties of muons are so extraordinary that I think that there's just going to be a lot of interesting things which one can do with muons. Muon accelerators, in particular, have the potential to provide multi-TeV lepton-anti-lepton collisions and open up an entirely new regime of accelerators. So we've done a lot of work on R&D, so Merit, Mucal, Emma, and then finally mice. And their mice, we've demonstrated ionization cooling. And that's really one of the key technologies for muon accelerators. Thank you.
Fascinating talk on muons. Now, we'll get time for a few questions. Any questions? Yes, Peter. There's no microphone.
Right.
You'll pick up from the ceiling.
Right. So if you've got muons being stored in a circular arrangement, how many times, this is the sensible measure, can you have them going round if you've got them going fast enough? Because then you've got the time dilation, so
right. So I didn't touch on time dilation. That's it for the acceleration. So 2 microseconds is a lifetime at rest. Obviously, if we're going up to TeV, then muon mass is 100 MeV. So you get this time dilation effect. So the ratio of the energy to the mass actually is a multiplier for the lifetime. So I can't do it in my head, but I guess it's 10,000, right? So you get the lifetime increases by 10,000 when you accelerate up to TeV scale. So that's important. And then now the question is, well, how many times can you really collide those muons before they all decay away? So the answer is it's the operational the operation of the facility wouldn't be the same as the LHC. So what you're not doing is accelerating a beam over minutes storing the beam for hours, colliding, and then dumping the beam and doing another one. So that's not how this would work. Really, you're accelerating the beam over a millisecond, storing the beam for a millisecond, colliding it, dumping it, and then accelerating up another beam. So that's the sort of operational regime. I'd have to look up the exact numbers for rep rate and things.
Yeah, a millisecond still 1,000 times longer than a microsecond.
Yeah, right. Yeah.
Yes, right at the top.
What sort of center of mass energies do you think are realistic collisional?
Well, so there's no reason you can't go to 14 TeV. I mean, your limit is the magnetic field strength of your accelerator. 14 TeV has been demonstrated. They have the LHC. Why not? And you know, you wouldn't, because you can't use a synchrotron. You have to do a different technology. You would probably you'd have to rebuild the magnets. And if you're rebuilding the magnets, you would go to, you know, you'd use the latest kit, and so you'd probably go up to 30 TeV, you know, or whatever magnets they can do, 20 TeV if that's what they can do.
Yes.
How come muons do not produce synchrotron radiation?
Right. So synchrotron radiation is produced by low mass particles. So because muons have very high mass relative to an electron, they don't produce synchrotron radiation. So it goes as the mass to the fourth. So it's a very strong power of the mass. So muons just don't produce any synchrotron radiation until you start getting up to an energy which is 200 times the electron energy. I'd love it if we could do that. So.
Any other questions? Yes.
If you had multi-TeV muons, would you then, in a circular accelerator, would you then have to deal with very high energy electrons from when they decay?
So the electrons are okay. The challenge is actually the neutrinos, because so electrons you can shield, but neutrinos are hard to shield. So neutrino radiation becomes an issue. So let's say if you go up to TeV, then the neutrinos, the decay neutrinos, start to have energies, which means you're approaching electroweak unification. You know, so you have to worry about neutrino radiation, and so the way to deal with that is to dig deep. So LHC tunnel, for example, is 60 meters deep, and so that's which means that the radiation is shielded by the Earth's crust.
This is a comment. The laser people were doing experiments about a year ago, and they were trying to generate muons from a laser. And one of the applications would be, to look at, say, nuclear proliferation, for instance, someone bringing some kind of nuclear material into the country, etc. So is there any connection between the work you've been doing and the laser work, or have you been talking to them?
I did invite one of them to come and have a chat to me, but he never did. So,
But in the audience now, I can recognize one or two.
But no, I mean, certainly that's interesting. So one of the things we proposed doing with the mice beamline after it was finished was actually looking at muon tomography. Yes. So muon tomography, I did have the slide and I took it out, but what you do is you put a muon through a material, you measure the muon track ingoing, and then it hits the material, scatters off. You measure the muon track outgoing, you just join the dots and figure out where that material was. And so that way you can look inside a cargo container or something like this and try and figure out whether there's any high mass objects which shouldn't be there. So it's an interesting technology. And you can do it with cosmic rays, but the rate's very low, and you would want higher rate, which means using more muons. So then you need an artificial muon source.
I'd encourage you to continue talking to the CLF people, because they're building EPAC now, and EPAC should be able to produce a considerable number of muons, actually.
Yeah.
And your experience will help there.
Yeah.
So I think with that, we'd like to thank the speaker again, and